All right, so in this video, we're going to be talking about systems of linear equations in several variables. So I think maybe we need to be a little bit more specific with this. We're going to be looking at specifically linear equations in 3 variables. The previous section was only 2 variables. This one will be 3 variables. Anything larger than 3 variables, like 4 variables, which means 4 equations, 5 variables, 5 equations, and so forth. On the surface, that can change, all right? But on the surface, we would be using matrices or something like that, all right? Which is actually the next video. So for us solving systems of linear equations in several variables, specifically 3, there's going to be 3 rules that we need to know. The first rule, you can add any 2 equations that you want together to form a new equation. All right. The second thing, you're allowed to multiply an equation by a non-zero constant. All right. And then the third, you can interchange any equations that you want. All right. Now, in the sense of solving a system of 3 equations, it's actually not that difficult. And sometimes you may be doing one of these rules or 2 of them, or maybe all 3. It all depends on what you're looking at. So what I have here is I have a very simple system here, and it's going to be x minus 2y plus 3z equals 1, x plus 2y minus z equals 13, and then 3x plus 2y minus 5z equals 3. Okay? Now, we've never seen a problem like this in the sense that we have 3 equations and 3 unknown variables. However, we do have techniques for a system with 2 variables and 2 equations. We can graph it, we can substitute and solve, or we can use the addition elimination method. So our goal here is to create a system of 2 equations. And it's actually much easier than you think. So here are the proper steps on how we do this. Step 1, you're going to choose a variable to eliminate. Okay, so just like in the system of 2 equations, that addition elimination method, you're going to do the same exact thing here, except you are specifically asked to just choose a variable to eliminate. So you're going to be looking for opposite signs, same coefficient. So I'm going to go ahead and I'm going to label my equations. This is equation 1, this is equation 2, and this is equation 3. All right? And if you notice, in equations 1 and 2, I can eliminate the y very easily. So we're going to choose equation 1, x minus 2y plus 3z equals 1, and equation 2, x plus 2y minus z equals 13. And we're going to add these 2 equations together. And when we add them together, x plus x is 2x, negative 2y plus 2y is 0, and then 3z minus z is going to be plus 2z equals 14. And what I like to do is I will put this in a box, and then I'm going to label this equation 4. And sorry about that. I'm going to just go ahead and maximize that again. All right, so there's step 1. Step 1 was just pick 2 equations, eliminate a variable. Step 2, we're going to eliminate the same variable in 2 different equations. All right. So we're going to have to eliminate the y again because that's the first variable we eliminated. So we're going to have to do it again. However, we're going to pick two different equations. So if you look at what I've done, in step 1, I eliminated the y in equations 1 and 2. Now in step 2, I can choose equations 1 and 3, or I can choose equations 2 and 3. Now, I'm going to go ahead and choose equations 1 and 3 because equation 1 is x minus 2y plus 3z equals 1. And then equation 3 is 3x plus 2y minus 5z equals positive 3. So I'm looking for, like I said, opposite signs, same number. So we're going to go ahead, we're going to add these together. X plus 3x is 4x. Negative 2y plus 2y is 0. 3z minus 5z is going to be minus 2z. And that's going to equal 4. So here, I have equation 5. Now, step 3. If you look on the board, it should kind of jump out at you, which is using equations 4 and 5, solve the system. So if you look at equations 4 and 5, equation 4 is 2x plus 2z equals 14. Equation 5 is 4x minus 2z plus 4. If you notice here, we have two equations, two variables. More importantly, the variables are the same exact variables. And we have a bunch of different ways that we can solve this. Right now, I'm looking at those z's. One's positive 2, one's negative 2. So I'm just going to add these two equations together. 2x plus 4x is going to be 6x. The z's will cancel each other out. 14 plus 4 is going to be 8. 18. Then we can solve for x by dividing both sides by 6 to give me x equals 3. And that's a beautiful thing. So we went from a system of 3 equations to a system of 2 equations to a solution of x equals 3. All right? Now, step 4, all we're going to do is backward substitute. Meaning, now that we know what x is, x equals 3, we're going to use x equals 3 and substitute into either equation 4 or equation 5. It doesn't matter. Regardless, we're going to find out what z is. So to keep this nice and neat, I guess I'm just going to go with 2x plus 2z equals 14. Since x equals 3, I'm going to substitute that in. And I just go ahead and solve. 2 times 3 is 6. Plus 2z equals 14. I will subtract 6 from both sides to give me 2z equals 14 minus 6 is 8. Then divide both sides by 2 to give me z equals 4. So now I know what x is. I know what z is. Our final step is use the original equation, or I guess I'll be a little bit more specific. Use one of the original equations to find the missing variable. So we know x equals 3. We know z equals 4. And we're going to choose one of the equations from above. It doesn't really matter. I'm just going to choose equation 1, which is x minus 2y plus 3z equaled 1. And I'm going to go ahead and make my substitutions. I know x is 3. I know z is 4. And we're going to go ahead and solve. So we get 3 minus 2y plus 12 equals 1. 3 plus 12 is going to be 15 minus 2y equals 1. I will subtract 15 from both sides. That gives me negative 2y equals negative 14. And then finally, divide both sides by negative 2 to give me y equals 7. So, x equals 3, y equals negative 7, z equaled 4. And right there are all the solutions to each variable respectively. Now, the big question becomes this. All right, now that we did this, what exactly does that look like? Okay, so because I am not an artist, I'm going to have to go ahead and just get our book out so you can see what that looks like. All right, so here's our book, and I'm going to go ahead and just steal this first figure here and put it into our notes. All right, so there we go. So if you look, what we just found was that right there. We found a point. The thing to remember here is this. When you have an equation, let's say it's x plus y equals 3, that can be graphed in a two-dimensional space, okay? That's going to be graphed in a two-dimensional space. So, in fact, that's not even the correct graph, but yeah, it is. It's close enough. So anyways, we call this, obviously, a line. Now, if you have x plus y plus z equals 3, you're no longer talking about lines. What you're talking about are planes, like a piece of paper. And the easiest way for me to draw that would be something like this. We know x and y, that's two dimensions or two different axes. However, when you have something with three variables, this is a point in space. So like I said, you're talking about space now, 3 dimensions, just like what you and I see as soon as we open up our eyes in the morning. All right. So what you and I are really used to, like I said, is right here. This is x comma y. All right. That's all this stuff down here. It's like putting an object on the floor and knowing exactly where it is. As soon as you incorporate that third variable, the z, what you're going to now do is instead of having an object, and I'm going to go ahead and change my color, my marker, and zoom in right here. Instead of this object being on the floor, what you're now doing is you're raising it up into the air and you're putting it in space somewhere. Okay? And that's what's happening with our solution right here. We have 3 equations. Each equation that we had is going to be the blue, the red, and that looks like yellow to me, yellow plane. The point at which all 3 of those planes intersect, in this case, it would have been 3, comma, negative 7, comma 4. That's where it would intersect. All right. Now, just like in systems of 2 variables, we also have the situation here where you can have different types of solutions. So in this first case, notice that the 3 planes intersect at a single point. So this system has one solution. We call that consistent, independent. Okay? Now, in part B, notice that all 3 planes intersect on this line that I'm shading in black. All right? This is a situation where you have infinitely many solutions. That is consistent again. Consistent meaning there's a solution. And it's dependent because there's infinitely many solutions. All right? Which means one equation is going to be dependent upon the other. And then finally, you have a system where you have no solutions. And that's because at no point or at no line do all 3 of these colors right here or all 3 of these planes that are different colors intersect each other. All right? So we would call this an inconsistent system.